I lost the video from Tuesday, so I am planning to make another one, so it'll be up. So to continue our discussion of fractals, we're going to talk about a new fractal today called Sierpinski's Triangle. It's also called Sierpinski's Gasket. You start with any triangle. It doesn't necessarily have to be equilateral, but it makes a nice shape if it's equilateral. Okay, and then you remove its middle. Okay, so you find the midpoint of all three sides, midpoint, connect them, and then you take this middle part and remove it. Get rid of it. Okay, so you're left with this thing at step C that has an empty middle. Now you have 3 orange triangles. You do the same thing to all the orange triangles to get to step 2. So you remove the middle again. Remove all these guys. And you're left with step 2. And now we have 9 orange triangles. Remove the middle of each one, and you get step 3. So you're just always removing the middle. And you continue this way to infinity. You do this an infinite number of times. Just keep doing it over and over and over again. So after a few more steps, our eyes can no longer tell the difference between one step and the next. So this is the Sierpinski gasket at step 7, and step 8 would not appear any different to us because our eyes, eventually we're going to get to a point where you're just removing little pixels. So what you're removing is so small that they're just little pixels, and our eyes and our brains have this ability to fill in gaps. So if I draw something on the board, or if I write, this is why you can read other people's writing, because other people's writing is never perfect, but your brain is able to fill in little gaps. Like if somebody writes, you know, right, that this letter right here looks like nothing. Right? Maybe it's a U, but we know it's an A because our brain just saw the whole word play, right? So that's why we can't conceive of differences. And we use that technology all the time, or it's not technology, I guess our brains aren't really technology, but we take advantage of that when we build technology in terms of projecting images on like a TV screen. We use the fact that your brain can't perceive differences between little itty bitty pixels in order to encode images with the smallest amount of data possible. So rather than putting, 100 pixels in a little tiny region, we could put 78 maybe, and nobody can tell the difference. So we can encode less information. So after a while, the Sierpinski gasket looks the same to us at every step. And apparently I learned that I was pronouncing this wrong. It's Coke, not Koch. So like the Coke snowflake, you can't ever finish drawing the Sierpinski gasket because it's an infinite object. The actual gasket is the shape you would obtain after an infinite number of iterations, removing the middle of the triangles. However, despite the fact that this thing can't exist in the physical world, it can only exist in the abstract in our brains, there are still some things we can know about it, for sure, even though it doesn't exist. So one thing we can know, same as the Coke snowflake, is that it has infinite, universal, and exact self-similarity. So we can zoom in forever on any spot, blow it up, and it'll look just like the original. So we can zoom in on this little one, blow it up, looks just like the original. You can zoom in on this little itty bitty piece down here, blow it up, looks just like the original. Second thing we can know about it is that its perimeter tends towards infinity. So by perimeter, I mean, because there isn't really an outside, I mean if you try to trace the edge of it. So if I trace all the edges like this, right? And I measure the lengths of all the edges and add them up. I mean, that would be the perimeter. So do you believe that it's going to grow to infinity?
Technically, but it seems like eventually you're making such very small measurements. It's really hard.
Uh-huh. Yeah.
If you do it, eventually, yeah.
Yeah, if you do this forever, it seems like the perimeter would go to infinity. However, you're removing such small pieces, maybe the lengths that you're adding aren't significant. What were you going to say, Joe?
It seems to me that you're just removing pieces, so the substitute size, not all the little triangles, it's always going to remain the same size.
Yes, yes. So that's a good good point. So if you're only measuring the outer edges, and because that's normally what we think of as perimeter, right? Then we're just removing pieces, right? So the outer edges always stay the same length. True. But by perimeter, I mean exposed edges. Okay, so let me go back to this step 3 picture. So I'm just going to measure all the length of all the exposed edges, not just the outer edges, but every exposed edge. I'm going to measure the length of and add them all up. So it seems like every time I take out a middle, I'm adding a little bit of perimeter. Every time I remove a middle, I add some perimeter. I add this perimeter or this perimeter. So it does in fact go to infinity. Yeah, it takes infinitely long to get there, yeah. But it does grow. It just grows and grows and grows without bound. Just gets longer and longer and longer. Grows towards infinity. With the Coke snowflake, we did a little activity to show us that it grows, that its perimeter grows to infinity. I'm not going to do it with this one. You're just going to believe me, okay? But I want to think about what happens to the area. The Koch's, the Sierpinski gasket is made up of the orange part, right? So I keep removing some of it. At every step, I remove some area from the gasket. So if we look at step 1, from the seed to step 1, how much remains? 3/4. Yeah, I broke this into 4 triangles and I threw one away. So 3/4 I kept. I kept 3/4 from the previous area. So let's look from step 1 to step 2. What fraction from at step 2 still remains from step 1? Three-fourths, yeah. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I started with 12 little orange triangles, and then I threw away 1, 2, 3 of them. So I kept 9, and that's 3/4. So I took each of these orange triangles that existed at step 1, and I broke them into 4. Each one got broken down into 4 triangles. And I kept 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 12. So I kept 3/4 of my previous area. So step 2 to step 3, how much area do you think we keep? 3/4, yeah. So let's just see. Each of these orange triangles, I'm going to break into 4. Four smaller triangles. And then I'm going to keep 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I'm keeping 27 of them, and there were a total of 28, 28, 29, 30, 31, 32, 33, 34, 35, 36. I kept 27 of the 36 little triangles, and what does that fraction reduce to? 3/4. So it seems like to get from one step to the next, you keep 3/4 of the area, because we're throwing away 25%, so we're keeping 75%. So if I was going to write a recursive formula for the area at step n, how do I figure it out? Yeah, I heard a couple people say it. The area at the previous step, which we denote a sub n minus 1, times 3/4. So that's my recursive. And if I want to write an explicit formula, it's going to be 3/4 multiplying by 3/4 over and over again. So I raise it to the nth, but I need a starting amount, right? Yep, because I said to assume the area of the C triangle is 1. So we start with 1, and we multiply it by 3/4 over and over again, n times. And the way you represent repeated multiplication is with an exponent. 1 times 3/4 to the n. So what do you think will happen as we let n go to infinity, as we do more and more iterations? It'll get smaller and smaller and smaller. That sideways 8 thing means infinity, yes. So as you raise this to higher and higher powers, the area gets smaller and smaller and smaller. What's it approaching? 0. A sub n approaches 0. Because think about it in terms of if this was money in your bank account. If every week 25% of the money in your bank account gets thrown away, right? Your bank takes it as a fee or whatever. That would be awful, right? Yeah, because yeah, switch banks, right? Because your bank account is just going to go steadily down towards 0. If every week you only get to keep 75% of what's in your bank account, it's just going to go to 0 real fast. That's what happens here. The area of this fractal goes to 0 real fast. So remember, the fractal itself is something that can only exist in our minds, and it's what exists after infinite iterations. So what is the area of the Sierpinski gasket? 0. It has 0 area. Yeah. So when I say the Sierpinski triangle, I mean the one that you get after infinite iterations that can only exist in your imagination. The Sierpinski triangle has 0 area, but infinite perimeter. Yeah. Yep. After infinite iterations, there will be 0 area remaining. But infinite perimeter. Right? So area tells you how much space it takes up. So it takes up no space, but has an infinite perimeter. Yeah. Might as well be a line, no thickness, one end of the universe to the other. And the Koch snowflake was a fractal that has infinite perimeter but takes up finite area. So that was weird enough. But now we have infinite perimeter with no area. This is actually used a lot, this idea of using a fractal to create a really long perimeter and a really small area is used for antennas. Okay, so like a cell phone antenna, right? You know, you used to have to, pull it out, and it was like this really long thing. Now they have little tiny ones right inside the phone, and they're modeled after fractals that will have a really long perimeter, so it actually has quite a lot of length without having to take up space like it used to. So that's one place it's used. It's also used, I think, in a lot of like medical technology devices. I don't really know a lot about it though. You see it in nature sometimes. This is a shell that has sort of an approximation of Sierpinski's gasket in its design. Yeah, shells are. So this fractal shows up in the strangest places. You know, we have found ways to use it, but it also shows up in this little thing called the chaos game. So if you start with an arbitrary triangle and we'll label the vertices A, B, and C, and we're going to roll a die, and a roll of 1 or 2 is going to correspond to vertex A, and a roll of 3 or 4 means vertex B, and 5 or 6 means vertex C. So here's the game. You choose any point in or on or near your triangle. Any point. Roll the die. And let's say we roll a 2, and that corresponds to vertex A. So we have our original point here. We pick our original point. We put it anywhere, like right here. This is original point. Then we roll the dice, and we get a 2, which corresponds to vertex A. So what we do is I'm going to draw a straight line. You know, I'm going to use my imagination. I'll draw it now, but in the real game, you just draw an imaginary line from the point to vertex A, and you put a new point halfway between A and your original point. So this is my new point number 1. Because I rolled a 2, yes. And 2 corresponds to vertex A.
But if you rolled a 1, would it still?
1 would still correspond to vertex A.
And it still would be.
And it would still be halfway point, yep. Okay, so then you just keep doing this, right? Roll the die again and put a point halfway between the last position and the new vertex that your die told you to use. So let's say we roll again and we get a 5. That would correspond to vertex C, right? So I use my most current point, draw an imaginary line to vertex C, and I put a new point halfway between the 2. So this is new point number 2. And then if I roll again, and let's say I roll a 1, right? If I roll a 1, that corresponds to vertex A. I draw a line to vertex A and put a new point halfway between. So this would be new point 3. No, we're not going to keep doing this. But this is the game, okay? So if we keep doing this, I have several steps done out here. Starting point, new point. This is just some diagrams showing how to get the new points. So now I'm just going to keep doing it. Keep doing it and doing it and doing it. What does that look like? It looks like the Sierpinski triangle. No, you don't actually draw the line. You just put the point. Yeah.
No, is that a guarantee every single time?
Every single time.
Like, who has time to do this?
I know, really. I want to know who discovered that. I think that's crazy.
Like,
I can't believe that shape comes out. Why would that happen? So I have a a cool little applet that shows this happening in real time, right? We have, it's called the chaos game because it totally depends on chance, yet we end up with this really structured object. All right, so here I have my triangle. I'm gonna, this little applet will play the chaos game for me. So I'm gonna start where it runs pretty slow, and you can see the game being played here. It's rolling, it doesn't show you the dice roll, but it's randomly choosing a vertex and placing a point halfway between. And actually, I'm going to show iterations so that you can see it drawing the line, and then the line just disappears after. All right, so this is kind of slow, so I'm going to speed it up a little bit. Yep, so now we're playing the game really fast. Yeah, it does. You have to play the game for a while before you start to see the pattern. And it's filling in the Sierpinski gasket. I just can't believe it. Like, really, this blows me away every time I see it.
Conspiracy. Aliens did it.
Aliens did it, yeah. All right, so I said it shows up in the randomest places. That's one place. Like, who would have ever thought that this random game that depends on chance would develop that shape? Okay. So another strange place that we're going to see Sierpinski's triangle show up is going to require a couple of slight detours. So this is going to seem unrelated for a couple minutes, but then I'll bring it back around. So this is something called Pascal's Triangle. Anybody see a pattern in here? There's a lot of ones, yeah. There's ones all down the left and the right far diagonals. Yeah, two numbers next to each other equal the number below and in between. So 1 plus 1 gives 2, and 1 plus 2 gives the 3, and 6 plus 4 gives 10, 15 plus 20 is 35. So this is Pascal's triangle. That's how you build it. You start out with 3 ones, right? And then each number you put in the triangle is the sum of the two numbers above it, and you always keep ones on the outside. So here you have 1 and 1, it's 2, and you keep ones on the outside. 1 and 2 is 3, 2 and 1 is 3, keep ones on the outside. 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4, and keep ones on the outside. Does this make sense? Okay, so this is how you build Pascal's triangle. And there are like millions of patterns in here. You could look at this thing, you could spend days and days finding more patterns in this thing. Yep, so you found the reverse of the addition pattern. Yep, so you can work backwards with subtraction. There's something called the hockey stick pattern or the sock pattern. Draw any hockey stick or sock in the whole triangle, add up the parts in the leg part, and it equals the part in the toe. Oh wait, I have to go all the way to the edge. I have to go all the way to the edge. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. You can do it anywhere. So I want to. No, it has to go from. It has to start at an edge. Has to start at an edge, but it can be any length as long as you start on an edge. So like there's a short one. 1 and 5 make 6. The Fibonacci numbers are even in here. So the Fibonacci numbers come from adding in a special way. Okay, so if I follow the diagonals, ready? So I'll show you. So if I go like this, if I draw that diagonal and add all of the hexagons that I went through, what's the sum of that first one? 1. Okay. So then I'm going to do the next one here. What's the sum of that one? What's the sum of that one? 2. 1 and 1. I just went through 2 hexagons, right? This one and this one. I get 2. Then this next one, I went through the 1 and the 2 and I got 3. And then
Disgusting.
this one I went through 1, 3, and 1 and I got 5. And then the next one, I went 1 and 4 is 5 plus 3
I really
is
hope someone told you that.
8.
You found that out all by yourself.
No, somebody told me. And then I have 1 plus 5 is 6, plus 6 is 12, plus 1 is 13. We have the Fibonacci numbers.
That's insane.
It is, that's crazy. Yeah, it even kind of looks like it spirals up like the spirals on a pineapple. Yeah. Yeah, that is cool. I never really thought about that. What happens if we just add them up across? Let's see what happens if I do this. If I just go like horizontally, I get 1.
2, 4.
8.
Can't see.
And now we have exponential growth, right? It's like tying everything that we know together. It's crazy.
Oh, yippee.
And
This for a project?
sure, yeah. If you want to change your project, you can do this. Yeah. So, and I've only spent 5 minutes showing you a couple of the patterns in here. It's just a really cool thing, and you could Google it. You can find millions and millions of cool stuff about Pascal's triangle. But I'm going to bring it back around to Sierpinski's gasket. But before I do, I have to talk about the arithmetic of remainders. So do you remember when you first learned division, like in 4th or 5th grade, and you always just wrote remainder 2,
Yeah.
right? You didn't know what to do with that thing? Yeah. So we're going to just go back to that today.
Can you remind? Remainder 2 is like point blah blah blah.
No. Yeah, it's just how much is left over, and we usually convert it to a fraction, but we're not going to today. Okay, so let's say I divide 20 by 6. I want to know the remainder. All I'm interested in is the remainder, but to get it, I have to actually do the division out, right? So you say, well, 6 goes into 20 how many times? 3, and 6 times 3 is 18, and my remainder is 2. Okay. So when I do 20 divided by 6, and I just want the remainder, the answer is 2, right? Because all I want is the remainder here. Only interested in the remainder, not actually how many times it goes in. Just want to know how much is left over. Okay, what if I do 28 divided by 7? What's my remainder? 0, because 7 goes into 28 exactly 4 times. So my remainder is 0 there. What if I divide 2 by 4, right? I'm going to do 2 divided by 4. What's my remainder? How? It cannot, right? It goes in 0 times, right? So if I tried to carry out this division, I would say, well, 4 goes into 2 0 times. 0 times 4 is 0. When I subtract, That's the remainder, right? Yeah. 2 left over. Okay. So if I want to divide 2 by 4, my remainder is 2. It goes in 0 times with 2 left over. All right, so let's say I want to divide some random number by 2. Any number, pick a number. What are the possible remainders I could get? Yeah, explain. Why just 0 and 1?
Because if you're dividing by 2, all you need is a 1 to make it even. You can divide by 2, and if you're dividing perfectly, your remainder is 0.
Okay, so if the number is divisible by 2, your remainder will be 0, right? So if it's even, so pick some numbers that are multiples of 2. I could do 14 divided by 2, and I get remainder 0, right? Any even number will be remainder 0. And any odd number, like 15, I get remainder 1. Because I can't get remainder 2, because if I had a remainder of 2, exactly, that would mean that 2 could go in again, and I would actually have remainder 0. Okay, so my only possible remainders, if I divide by 2, are 0 and 1. 0 corresponds to an even number, and 1 corresponds to an odd number. Yep. Those are the only possible remainders when you divide by 2. What if I want to divide a number by 3? What are the possible remainders? 0, 1, and 2. Why not 3? Because remainder of 3 is the same as remainder of 0. Because if you get a remainder of 3, that means 3 could have divided in a whole nother time. Yep, so my only possible remainders would be 0, 1, and 2. Now, in this case, we have special names for the remainders. Remainder 0 was even and remainder 1 was odd. We don't have special names here. Okay, these guys don't have special names. All right, so my activity that I want you to do is take each number in Pascal's triangle and divide by 2. If the remainder is 0, that is if it's even, color the hexagon one color. And if the remainder is 1, that is if it's an odd number, color it a different color. So you could just use, let white be one of your colors if you don't have pencils or crayons. Yeah, you could do lines in one and a shading in the other or something like that. See what it looks like after you're done. So it's related to the chaos game. It's in nature. And we see it in Pascal's triangle, which also has like a million other patterns. And we see it in Pascal's triangle related to division and remainders of division. And it's also fun to do this for any other number that you divide by. If you divide by 3 and you color the remainders of 0, 1, and 2, 3 different colors, you see Sierpinski's triangle again. It's just a more colorful version. And if you divide by 4 and you color the remainders 0, 1, 2, and 3 different colors, then you see Sierpinski's triangle again.
Probably gonna need a bigger triangle.
You need a bigger triangle, yeah. Yeah, exactly. All right, so the last thing is called the twisted Sierpinski gasket. So this is where we do the same process to create as we do to create Sierpinski's triangle, but at each step we have a little jolt, right? So we have our seed, we remove the middle, then we do a little jolt. We move these midpoints just a little tiny bit. Okay? A little tiny random amount. Okay? And the effect is though the triangle has been jolted as if in an earthquake. Okay? And earthquakes are the very things that make mountains, right? So I'm doing Sierpinski's gasket and I'm applying a little earthquake at each step. So you remove the middle, apply the jolt, continue to infinity, and you get something that looks like this. It looks like a mountain.
Language of the universe.
Uh-huh. Math, I like that. Math is the language of the universe. All right, so because of the randomness of the jolt part of this process, the self-similarity of the twisted gasket is infinite and universal. You can zoom in forever, and you can zoom in anywhere, but it's approximate and not exact. Okay, because each jolt is a little bit different than the last. So zooming in won't give you exactly the same picture as the original, but it'll look the same. It'll look pretty close, yep. So here's your homework. And if you're interested in fractals, the next section of your text you might be interested to read is called the Mandelbrot set. And this is probably the most famous fractal and the most recently discovered, right? So you might want to read about that if you're interested. And if you're not, don't read it. So you could start your homework now, but please don't leave because another professor is coming in like 3 or 4 minutes to give you course evaluations. Sorry. Yes. What? No, because someone might leave. Someone might sneak out if I leave the class. Oh, yeah, sure.